Okay, the bungee jumping project. So here's the idea. You got, say, your river down here. You got some bridge up here. I'll label all this for you. And here's the river. And you got your person up here that's going to bungee jump. They're going to come down until they reach the end of the bungee cord. So right here, this is the cord. And then they'll swing down and back up. During this entire phase, the cord is being stretched. Once they reach back to this level here again, then up in here, they're in free fall again. So they're in free fall here. We have some kind of spring constant here, and then we're in free fall again up here. Now, everything works out a lot easier in this project if we call down the positive y direction. So down is positive y. And we're going to call right up here at the bridge y equals 0. And let's say the river is 100 meters. And let's say our cord is 50 meters long. Okay, then here this would be t equals 0 up here. And then down here, let's call this y0, y2, and right here, y1 will be 50 meters. This is when you've reached the end of the cord and the cord starts to stretch. Stretch. Okay, so at first, for for the time period from T0 to T1, you're in free fall. So, like weird, if you've taken physics one, you already know what we're going to get. We're going to get y equals 1 half at squared, but like we'll quickly go through it. We know the sum of the forces equals mass times acceleration, and acceleration is the second derivative of position. And in our free body diagram, the only force acting on us, we're ignoring air resistance here because everything happens so quickly. There's really no air resistance to speak of. Our only force is weight, which will be mg. And you might think, wait a minute, isn't that supposed to be negative mg? No, we call down the positive direction. Then we don't have to deal with a bunch of negatives. Now remember, or I already said that here, y double prime. M's cancel. You get y double prime equals g. Now, bunch of different ways we could solve this. We could just integrate both sides. Second derivative of some function is just a constant. That function, it's a g there. It's just a quadratic. So up until T1, up until the cord starts to stretch, we're just in free fall. And it's independent of the mass. Okay, so then after T1, so from T1 to T2, this is the time from, again, when the cord starts to stretch until we reach the end and it's stretched all the way out. Now we have another force. So again, we'll draw a free body diagram. We'll have our weight pushing down, and we'll have some spring force. We'll call it Fs pointing back up. But remember, down is the positive direction. So this will be a positive force. This will be a negative force. So sum of the forces equals mass times acceleration. So we'll have mg in the positive direction minus, well, what's our spring force? Fs is negative ky, where y here is how much we've been stretched. So let me pause a second. Okay, so Now we want to make sure we get our sign right here. The spring is pushing us in the opposite direction. If we're down here, the spring is going to push us back up. So these are negatives because the top, remember, this side is the negative side, this side is the positive side. So yeah, this is right. I wanted to make sure I had that sign right. Yeah, that's going to push back up. It's stretching, pulling us back up. Now, we got to be careful here because when I say y here, I do not mean this distance. I mean just this distance, how far we've been stretched. So there are a couple ways we could do this. I could, like, I know how long the cord is. I could say here y minus 50. So that say y is 55, we've been stretched 5 meters. That would work just fine. That's one way we could do it. I don't think I've ever had a group do it that way. Hold on, let me think about this. This is interesting. I've never had a group actually do it that way, and I think it might be better. Let me think. Okay, yeah, I had to think about this for a minute because I've always done this a different way, and I think this way is going to turn out to be easier. So we could restart our clock. This is the way groups have always done it in the past. Call just for a moment this location right here, the new y equals 0 and the new t equals 0. Solve the dE, and then shift everything over. Replace all of our t's with p minus t1 to shift our time, and replace our y with whatever we get plus 50 to get my new y. It works out fine. I'm starting to think it might be easier to do it this way because what we want right here is how far the cord has been stretched. So this is 50 here. If I'm down in here, the cord has only been stretched the total y minus 50. So here in my dE, we're going to have this. So remember up here, y0 is 0. V of 0, which is y prime of 0, is also 0. Now we've got this dE, my double prime equals mg minus k times y minus 50 with the initial conditions. Y at t1 is 50 and v at t1 will be y prime at t1. So we're going to have to find this. We're going to have to figure out how long it takes to reach where the cord starts stretching, but that's pretty easy. So to find T1, we just set 1/2 GT squared, T1 squared equal to 50 and solve. I mean, it's pretty easy. Multiply over the 2, divide by G. You get T is going to be what? Square root of 100 over G. That's T1. Now, how are we going to find the velocity? How fast are we going when the cord starts to stretch? Well, velocity is just the derivative of position. So take the derivative, you get v of t, and 2 times 1/2, you just get g times t. So V at T1 would just be G times T1. Sorry, I know this is getting a little messy. Make sure this is right. Yeah, that looks okay. Okay, so we have T1, we have V at T1, we know Y at T1, now we know V at T1. So this is our initial value problem we're trying to solve. This is a non-homogeneous second order dE with constant coefficients. We could multiply through there by this negative k, negative ky, and then what do we get? Plus 50k. Move this guy to the other side. This is just a constant. So we would solve the homogeneous version of this, set that equal to 0. We get our characteristic polynomial. Like it's pretty obvious what you're going to get. M lambda squared plus k equals 0. So lambda will be plus or minus the square root of k over m times I. We get sines and cosines and exponentials. Or just our exponentials are e to the 0. So we just get sines and cosines. Then we assume a particular solution, assume yp equals a constant, some a, and solve for a. Second derivative of constant of 0, I mean, it's pretty obvious what we're getting. We get ka. Yeah, this is much easier than the other one. A times k equals mg plus 50k. Divide through by k, you get a is mg over k plus 50. So then I'm pretty much done most of it for you here. So you get your solution with the C1, the C2, and you're going to use these conditions to solve for C1 and C2. Again, there are other ways we could do this. We could shift our clock just for a moment, call this time 0, make solving for C1 and C2 a little easier, and then shift the function over by, I think this turns out to be like 2 seconds or something. It's like 2.9 seconds. Or we could just use these numbers. Okay, so then we're going to have our new solution. And we're going to graph all this together. We're going to graph a piecewise defined function. So y is going to be that y number 1, the free fall, up until t1. So from 0 up until t1. And then y2, the one we just found, up until, say, t3. What did I call it up here? Maybe I called it t2. t0, this was t1 here. I'm going to call this t3 because we're going to find this at some point. The how low we go, let's call that t2. Okay, and the easiest way to graph this as a piecewise function is to do it in Desmos. So use Desmos to draw a graph. You're going to have to look up how to do piecewise functions, but I'm actually going to show you. And notice I haven't given you m, g, or k yet. Our goal here is to figure out what kind of k value I need on my cord so that we don't hit the water. So we're going to start with a typical mass, maybe a 50 kilogram person. So that might be a teenager. Some K value like 15 newtons per meter. and we're going to see, do we hit the water? And we're going to play around with different masses and different K values and see which ones hit the water and which ones don't. And it's possible to program all that into Desmos. So your solution is going to look a little bit different, I think, than what we got here. But here you can see we're doing this is how you do piecewise. And I don't remember like what chord length they used there. I think they did use 50 because they got something similar there. So maybe T1 was 3.19. And then we can see here, you're going to get a solution that's probably something like this. And you put in some limits on here in these braces, so we'll only graph certain parts. And they went a little too far here. So remember, our graph is upside down. Up is positive. Here's the bridge, and the river is right here at 100. This is at 50. That's when, so we're falling. This is all free fall, and now the chord starts to stretch, but we should stop this right here because once the chord is stretched, you reach the bottom, you come back up. Once you're back up in this section again, you're in free fall again. A regular spring, if you compress it, it'll push back against you. A bungee cord's not going to do that. If I kept this model going, if I kept this graph here right in this section, the model is assuming that bungee cord is pushing you back down, which it doesn't do. So we would want to cut this off over here when it hits 50 again. You would have to find that. But notice how when they type this up, this is an old group, they left the K's and the M's in here so that we can do adjustments. Look, at that mass, I'm going to hit the river. But if I make my K, if I make my bungee cord stiffer, now I'll no longer hit the river. So this is the game we're playing. We're figuring out at least three different scenarios. We're going to pick some different M's and K's where we do and don't hit the river. Maybe one where we don't hit the river, one where we just touch the river, and one where we're we're going to drown. That's our goal. Make sure when you do this, you label your graphs, and then you can always come up here into Desmos and you can export an image. In each one that you export, though, make sure that for each individual graph, you figure out this time there so that you can stop the green graph right there when it hits 50 again. Okay. So your goal here, I'm going to write this down. Produce a few different graphs. Where say one, you don't hit the water. Two, just touch the water. And three, really hit the water. Go into water, let's say. That says water. Okay, so just quickly going through the whole thing again. You're going to type all this up in all the gory detail into a Word or a Google document. You're going to want some kind of image here. If we were publishing this paper, you would want a professional looking image. For the purposes of this project, it's okay to hand draw something. It's okay if it looks ugly. But have some kind of image with some labels on it, like something along the lines of what I have here. Clearly explain what's going on. Do the free fall section. Like go through this math, make sure you have a free body diagram, use your initial conditions, solve the DE. I think it's perfectly reasonable to just say we all know from physics one that the solution here in free fall is 1/2 GT squared. But still go through this physics. Solve for T1, the time when this equals 50. Solve for V1 to find your velocity at that time because you're going to need that. Then move on to the section when the cord is stretching. Draw a new free body diagram. Here's Newton's second law. Explain what's going on here. This is Hooke's law. Let me write that down in here. Hooke's law. And Hooke's law says that the force on a spring is proportional to the amount it's been stretched and will point in the opposite direction. That's why there's a negative. It's pulling us back up, but up is negative. Then you're going to talk about this second order non-homogeneous DE. You're going to solve it again in the paper, go through all the gory details. I will mention here there is an alternate way to do this, and I'll leave it up to you as a group which way you want to handle your initial conditions. So you could do this, like T1, it was 3 seconds, whatever that was. Here are your two initial conditions. Solve for C1 and C2 that you get that go with your sines and your cosines. Or it's one or the other. Don't do both. Or restart the clock. This will make solving for C1 and C2 easier. But there's this extra conceptual jump here about restarting the clock. So call this new time just for a second 0 and do y of 0 equals 50. V of 0 equals whatever you got up here, V1. Then once you get your solution, you get some y of t. We're going to shift that by replacing every t that you get in your answer with a t minus t1. So now we're going to shift over by that time. So you're going to get some solution that might look like y of t is some number times cosine of t minus 3.2 seconds plus some sine of t minus 3. All the t's now are replaced with t minus 3.19, whatever that t1 time is. This will make solving for C1 and C2 easier because you get to use zeros instead of 3.19. But then there's this conceptual step of, okay, now we got to shift our clock back over. Or alternatively, I mean, it's not too bad here. You solve a system of equations using these two values. And as a group, decide which way you want to do it. Like I'll show you here, this other group did it. See, that's what that is right there. They used X instead of T. I would use T as my variable, and I would have called this Y equals, and I would have made this T, and this would be T. Like obviously you got to change them all, but that's what they've done here. They've done this shift and show you in their paper where that shift is. See, right there. And then we're going to solve for T2, solve for T3. You can do that numerically because we do get a what we call a transcendental equation. It's pretty much impossible. I mean, I guess you could use calculus, take the derivative, set it equal to zero, find out when velocity equals zero, but it's going to be a really ugly equation. Figuring out when you reach the maximum, we can just do numerically looking at the graph here. Similarly, figuring out when we get back to unstretched length, when we get back to 50, we can just do that numerically. Just kind of drag along here until we see when we're back at 50 for whatever scenario we're in. Okay. All right. So how are you going to do this whole project? In the paper, you're going to type up all these gory details. Whichever system you decide to use here, make sure it's clear to the audience. Make sure you have free body diagrams. Make sure you have at least 3 different graphs where each graph is clearly explained what's going on there. And then the whole point of having a graph is to have something to talk about. So you'll write a sentence or two. We can see in this graph with k equals this and m equals that, we do not hit the water and so forth. Make sure your graphs are labeled. So everything goes into the paper. I would recommend using Google Docs to type up your paper. So here in Google Docs, you can share with each other. You can add on this extension called Auto LaTeX equations. You do have to type up all your own mathematics. You're all probably engineering majors. You're going to have to learn LaTeX at some point. Now's a good time to start. So here in this extension, you can see here they tell us in the directions, all the math has to be embedded inside these dollar signs. So I could say, what was my D? Y double prime equals mg minus k, and then what do we have? Y minus 50, I think. And then I can hit render, and it'll give me a nice, beautiful equation. You don't have to hit render every time you type an equation. You could literally type the entire paper and hit render all at the end. I recommend typing 2 or 3 equations, rendering them, because you're going to make mistakes. If you make a mistake, highlight it and go back. Like make sure the cursor is right before there and hit de-render, and then you can edit. Okay, so all the details are here in the paper. Your presentation is only going to be 10 to 15 minutes long. I would rather see 9.5 minutes than 15.5 minutes. If you ever do like a formal presentation at some conference and they give you 15 minutes to do your presentation and you go 16 minutes, they will never invite you back. It is a faux pas. It is rude to go over your allotted time. So make sure you do not go over 15 minutes. In the presentation, we're just hitting the highlights, the stuff that's, relevant to this course. You're going to explain the physics. Like you're going to have this image up on a slide. You're going to explain to the group what's going on. Quickly, like this part here is boring. You have your free body diagram, your physics 1, free fall, kinematic equation here, pretty boring. Maybe a slide showing finding these values. I'm maybe a minute and a half into the presentation by the time I get to here. You could even throw up a graph right there if you want, just for that free fall section. You could have just this little graph here if you want, but don't spend too much time yet. Now we're going to draw another free body diagram. You're going to show that on a slide, explain what's going on here, explain what Hooke's law is doing. Here's where we're going to spend much more time. Again, just hitting the highlights though. You never, ever, ever want a big chunk of text or a big chunk of math on any slide. You never want a slide full of stuff. And absolutely never read to your audience. That is my number one rule. Do not read to your audience. I see it all the time. Somebody will present a slide and they'll have a whole paragraph of text, and then they'll just sit and read that to me. I learned how to read in elementary school. Do not read to me. It is rude to your audience. Other times people they'll have like a normal looking slide, but then you'll hear them. They obviously have note cards in front of them, or they have the paper in front of them. And they're just reading this big giant paragraph of text. And it's obvious when you're reading it, it is so boring. Learn your presentation. Don't memorize it. I would rather hear you stutter and stammer than hear you read. It's okay to mess up when you're speaking. You hear me mess up when I'm speaking all the time. That makes for a more interesting presentation than listening to somebody read in some monotone voice. Similarly, you never want a whole bunch of math on the screen at one time because nobody's listening to you. They're trying to look at all the math. So maybe one or two equations at most on each slide. And then just point to stuff. Whoever is talking should be the one in control of the mouse. And you point to stuff. Do not my double prime equals mg minus k parentheses y minus 50 parentheses y parentheses t1 parentheses equals 50 v parentheses. You're already bored. Imagine that for 6 minutes straight. Here's our dE. Here we get Hooke's law. Remember Hooke's law? The force is proportional to how far the spring has been stretched, and this is how far it's been stretched. There's our K value. If we move everything to the other side, we get this dE here. This is non-homogeneous. Here's our characteristic polynomial. Here are the solutions to it, and then we get our sines and cosines, blah, blah, blah. Like just point to stuff, don't read it all to us, but have all the important stuff in the presentation. If you are doing this shifty thing here, you're definitely going to have to explain that to the audience. That's not, it's kind of counterintuitive what's going on there. If not, if you're just plugging in the T1 values, again, don't spend too much time on the boring details of solving that system of equations. Throw the system up there on the screen and then say, here's what we got for C1 and C2. And then I would say, like, if you want to see all the details, they're in the paper. You're going to have several graphs. Make sure you talk about each graph. That's the whole point of putting a graph. Make sure your graphs are labeled. I would even then, with this project, during the presentation itself, build an applet like this here in Desmos so that you can come in and play. Like you can literally see how they did it here. And then during the presentation, play around. Now, they're not going to cut off here at 50 like they're supposed to if you're playing with them. That's okay. Like during the presentation, I don't expect it to, I mean, I guess you could solve algebraically where it's going to cut off and put that in here in terms of M, K, and G so that they always cut off at 50. But that's not necessary if we're just playing around here and you're saying during the presentation itself, okay, you could see at this K value, we don't hit the water. Then we touch it. Now we're in the water. But for the individual graphs that you produce, the ones that you stick in the paper, the ones that you show during the presentation, do make sure they stop here when this hits 50. Okay, how are we going to type this up? We talked about auto law tech equations. So type up the entire thing. It should have a bunch of pictures in it. Now we're going to make our slideshow. Listen, I could not even possibly care less about all the fancy transitions and the backgrounds and all that. If you want to make your slideshow pretty and have all the fancy animations and all that, be my guest, but you're not going to get extra points for that. I wouldn't waste my time with it. I'm perfectly fine with a every slide is white background and black text. And then of course your images. You can type math here in the slideshow, but my recommendation is type everything up here in the paper first, and then just copy and paste the stuff that's going to go in the slideshow. So like here, this equation, I could just highlight it, Control C, come over here, Control V, boom, I'm done. Move it, resize it where I want it. Got an equation in here. Probably want more slides than you think. It's better to have three slides with one equation each than one slide with three equations. I mean, sometimes you need more than one on a slide, but don't overwhelm it. Don't overdo it. Remember, everybody in the group is responsible for the entire project. I know you're going to split the work up somehow. Like maybe one person will do all the math, one person types up the paper, one person does the slideshow and all the graphs, and you'll figure out how to split up the work. But when I go to grade it, I'm grading everyone on the entire project. So you might think, oh, well, the group agreed that I was going to do solving this non-homogeneous DE, and that's all I'm responsible for, and I know that part's right. Yeah, but maybe if there are typos in the paper up here, you're still losing points. I didn't do that part. Your name's on it. Everybody's responsible for the whole thing. So you have to check each other. I'm going to spend a lot of time in the next week or so talking about how we're going to make sure points get distributed properly. If somebody doesn't do their part, don't worry. If you have to do somebody else's part because they were slacking, you'll end up getting their points. We'll talk about that later. Everybody's responsible for the whole thing. Everybody has to present. Do not read to your audience. My number one rule. So I'm going to grade the group on the overall project, and then I'm going to grade you individually on your own presentation. If it sounds like you don't know what you're talking about, or if you read to your audience, you're individually going to lose some points. Okay, I think that's a good place to stop.